Okay, today we are returning to adaptive dynamics. So on Monday, we went through linear stability analysis. A recap of that for those who either weren't that familiar with it or who had forgotten about it. And today we are going to be talking about something called convergent stability. I'll talk a little bit about why this is a bit different from evolutionary stability in a moment. So far, in terms of adaptive dynamics, remember we've had this kind of recipe where we find some steady state for our ecological or population dynamics. We then introduce a rare mutation. We see whether that mutation can invade or not by looking at the invasion fitness, and we essentially keep iterating that process where if the mutant can invade, it replaces the resident and then becomes the new resident. Then we allow that to reach equilibrium, then we introduce a new mutation and then keep repeating. We can look at our selection gradient, which is our first order partial derivative with respect to our mutant trait of our invasion fitness. That tells us essentially if our selection gradient is positive, then our trait is going to be increasing, our phenotype, whatever it happens to be, will be increasing. If it's negative, it will be decreasing. And so if it's 0, then we end up with a singular strategy. We then look at its evolutionary stability, and that's telling us something about the curvature of our invasion fitness at a singular strategy. And we can work out whether it's a fitness maximum or a fitness minimum. If it's a fitness maximum, then it's evolutionarily stable. Okay. So one of the key things there, though, is that evolutionary stability only tells you at that particular point if it's a fitness maximum or minimum. You can think of this as being like a fitness maximum is the peak of a mountain and a fitness minimum is the lowest point of a valley. Okay. It only tells you that kind of height, if you like, that relationship to other traits nearby, so other phenotypes nearby. Is it a mountain peak or is it a valley? What it doesn't tell you, though, is if there's a path that will lead you there. Okay, so you can imagine that there's a mountain peak, but you can never actually get there. The reason we care about that is because we're doing this slow process, if you like, or gradual process of nearby mutation replacement, nearby mutation replacement. Okay, so you can think of that as like there being a path leading you to the top of a mountain or to the bottom of a valley. But there's not always a path that will necessarily lead you there. This is where convergent stability comes in, and this is actually a lot more analogous to what like the kinds of stability that you would have met in terms of like dynamical systems. Okay, so we'll be talking about that aspect today. So we're going to talk about some graphical interpretations as well today. These are called pairwise invasion plots. We'll talk about convergent stability. What happens if we have different types of singular strategies depending on the convergent stability and evolutionary stability. Depending on these combinations, we can end up with things called continuously stable strategies, evolutionary attractors or repellers, things called Garden of Eden singular strategies, and evolutionary branching plots. Okay, so we'll be going through these things today. So I'm just going to recap. I've gone through this a little bit already, but I'll just recap it here. Remember, with adaptive dynamics, we have a a phenotype or a trait. Here we could just think of it maybe as like a real number. It might be bounded and depending on the scenario you're looking at. And this trait value, we're assuming essentially that there are lots and lots of genetic loci that make up this trait. And each of those loci has a small additive effect. Okay, so when we have a mutation, you can think of that as like an allele flipping, but it only has a very small effect. Okay, so we are going to assume that those mutations are very rare. That allows us to have this separation between ecological and evolutionary timescales, and that simplifies the analysis quite a lot. And we're going to assume, like I said, that mutant is very similar phenotypically to our resident. So we can basically treat things as being continuous. Okay, so I mentioned that first stage is calculating our invasion fitness. And I'll write this as W of XM XR. This is saying the invasion fitness of a rare mutant with trait XM in an environment that is established by a resident population XR. Okay, so essentially this resident population is creating the conditions in which a mutant has to invade. And that's really a key thing about this process. This, in most simple models, we'll talk about next week, hopefully next week we'll talk about this as to why this isn't always the case. But in many simple cases, we can write this simply the per capita growth rate of our mutant trait when it's relatively rare. So the model we met before, it looks something like this. So we're evaluating this when our resident population is at its equilibrium. Sometimes we don't write that down because it's implied. Okay, so that's our invasion fitness. That's our stage one. Think of this as a bit like a recipe. We then find our selection gradient. This is sometimes also referred to as a fitness gradient. Essentially, they're the same thing as far as we're concerned. So this we write as S of XR, sometimes even just S of X. S of XR is just the partial derivative of our invasion fitness with respect to our mutant trait, and then evaluated when our mutant is equal to our resident trait. This is basically saying, okay, if we have a given value for our resident trait, that's why we're evaluating it at our resident trait here. If we introduce a rare mutant that is either slightly higher or slightly lower, is it going to be able to invade? In other words, is this positive or negative? Okay. It's basically saying, yeah, that like at that point, what is the instantaneous rate of change? It's a derivative, right? Okay, so the population is going to evolve in the direction of the selection gradient until we reach a singular strategy. So this is just like equilibria in a normal dynamical system. We want this selection gradient to be equal to 0 for some singular strategy X star. So like I said, this trait will be increasing if this is positive, X will increase if it's positive, it will decrease if it's negative. When the selection gradient vanishes, we're at a singular strategy. It's neither increasing nor decreasing at that moment. Then we say that a singular strategy is said to be evolutionarily stable if we take the second derivative, we call this E, our second derivative with respect to second partial derivative with respect to our mutant trait, and evaluate this with both our resident and our mutant traits at our singular strategy. If this value is less than 0, then our singular strategy is evolutionarily stable. Okay, essentially what we've got here, scenario that looks a bit like this. If we plot our invasion fitness, I'm essentially taking a slice through invasion fitness here because it's a two-dimensional function. If we imagine our invasion fitness here as we vary xm, it looks something like this if we're evolutionarily stable. This is xr, or rather this is x star. Okay, so this condition here is ensuring that we have a fitness maximum. If this was positive, then this black curve would be the other way around. So this is like the top of your mountain. Okay. Note that every other mutant nearby, all these guys here, nearby mutants, all have lower fitness. Right, their invasion fitness is negative. They can't invade. So as it says here, this condition here ensures that the singular strategy is a fitness maximum. In other words, it's uninvadable. So that should remind you of evolutionary game theory. Okay, but it doesn't tell you about convergence. Yes.
That was equal to 0. Would it just be a straight? Would it just be a horizontal straight line?
Yes. Yeah. Well, at least it would be. Let's say an inflection point at that point. Yeah. Okay. Any questions? No. Okay. So the first thing we're going to do today is we're going to think about graphical representations. So these are called pairwise invasion plots, or PIPs for short. And these can really help you to understand if you're having trouble visualizing what's going on with adaptive dynamics, these can really help. And all these do is they show essentially just the sign of our invasion fitness as a function of xm and xr. The way that I've written xm and xr, you can think of these as x and y coordinates. But actually, typically we would put our invasion fitness, with our mutant trait is along the vertical axis and our resident trait is along the horizontal axis. So you kind of have to flip these around in your mind if you're thinking about XY coordinates. But that's all we do. So what does this look like? Well, we can imagine a scenario that maybe looks like this. This is going to be my resident trait on the horizontal axis, XR, my mutant trait on the vertical axis. And then it's always going to be, first of all, this line here, this diagonal, and that's just the diagonal XM is equal to XR. So when our mutant trait is equal to our resident trait, by definition, our invasion fitness is going to be equal to 0. Okay, or if our mutant is exactly the same as our resident trait, it can't be more fit than it. It has to have exactly the same fitness, so it can't invade. Nor will it be driven extinct, it just is exactly the same. Okay, so this is our first line. And then depending on your selection gradient, there will be some other one or more other curves on here, potentially. I'll draw one like this. Usually we calculate these things numerically. So that is something that kind of comes out of solving these numerically. I'm not going to talk about exactly where this curve comes from, but essentially this comes from your selection gradient. And then because we just care about the signs, we can think about the signs of our invasion fitness in these different regions. Okay, so plus means W is positive, minus means W is negative. Okay. And then we care really then about what happens close to this main diagonal here. Can anyone tell me why we care what happens close to the main diagonal? Yeah.
Are we assuming that the entity is similar to this?
Exactly, yeah. So we don't really care about what's happening over here or down here, because that would imply that there's some kind of large mutation. What we're really thinking about is, okay, suppose we start here, this is my initial value. This is XM is equal to XR at the moment. Suppose I have a mutation that has slightly higher fitness up here. Or rather, I mean, that is what it has. A mutation has a slightly higher value of XM. In this case, it also happens to have higher fitness because we're in this positive region, okay? If that's the case, then it will be able to invade. And then we can repeat the process. Imagine a mutation has a slightly higher value of XM. Can it invade? Yes. And then you can carry this process on until you get to this point here. This happens to be this intersection between these lines is our singular strategy. Likewise, if you started over in this region here, in the top, if there was an X value that had a slightly, your mutant had a slightly lower value than XR, then it's going to be able to invade. And then you would staircase down like this again. So in both of these cases, this arrangement here, just by looking at this pairwise invasion plot, tells you that the singular strategy in the middle is convergent stable, right? Because we converge towards it. We'll talk about how we can derive that analytically in a moment, but I want to give you a bit of an intuition that this red dot here, this is our singular strategy because it's an intersection between these positive and negative regions, this main diagonal. In other words, our selection gradient is changing sign. And here we happen to be converging towards that central state. If, for example, I started up here and I have a mutation that gives me a higher value of XM, it's in this negative region. So that mutant can't invade, you just end up going straight back down to the main diagonal. Likewise down here, if I have a mutation that lowers my value of XM, it can't invade, I just end up straight back on the main diagonal. So this staircasing here is, it can suggest that there's a bias in the mutations, that here it's always a mutation that's increasing your value of XM. Really, it's saying these are the mutations that are able to invade. Okay. Any questions about PIPs? No? Okay. So like I said, intuitively, when the invasion fitness is positive above the diagonal, then that means that for some small value of epsilon, W of invasion fitness of our resident trait plus some small value. This is just our XM. An environment set by that resident trait is going to be positive for sufficiently small, epsilon greater than 0. This isn't necessarily true for all. As you can kind of see here, if I again zoom in, picture is getting a little bit busy now, but suppose I'm here. If the positive region above this main diagonal, sorry, this region up here is positive. So if I have a mutant that is slightly bigger, then we're in this positive region. However, if I go much bigger, I'm now in that negative region. Okay, so it only accounts for local effects. That's why epsilon has to be sufficiently small. So in this case, our selection gradient is positive, so XR, our resident trait, is going to increase. And then conversely, if we have our invasion fitness for XR minus epsilon, values of XR being positive, again for some small epsilon, our selection gradient is negative. Our selection gradient is positive, and so our trait decreases, sorry. So I've already said this, but how can we identify singular strategies from a PIP? Well, the intersections between these positive and negative regions along the XM equals XR diagonal. So along that diagonal that I've highlighted here in green. Otherwise, you can think of it really as, what I mean by that is when this this second line that I've drawn here, it might be a line, it might be a curve, whatever, whenever this is intersecting, it's telling us that basically as we're moving along this diagonal, at what point do we move? If we're just either side of it from a positive to a negative region, here I move from a positive to negative regions, there must be a singular strategy. Here I move from a positive to negative region, or vice versa. Okay. Yeah.
What is the other line?
The other line is essentially given by our selection gradient. It tells us, yeah, the way that this crosses is given by a selection gradient. Typically, I would not be expecting you to sketch these things by hand. Usually, we just calculate them numerically. That's why I've not dwelled on that too much. But I'll talk a little bit about how we know convergent stability based on those derivatives. Any questions other than that so far? Nope. Okay, so that's the kind of intuition behind this. So we say that a singular strategy X star is convergent stable if the selection gradient essentially points towards X star. That's all it means for it to be convergent stable. It points towards X star for sufficiently nearby values of X. So that just means that our selection gradient has to change from positive for X less than X star to negative for X greater than X star. So we think about, we'll call this C as our convergent stable. That means is our selection gradient, if we take the derivative of that with respect to our resident trait and evaluate this at our singular strategy X star, this has to be negative, right? Because it's changing sign from positive to negative as XR increases. But S, we had, I'll just go all the way back up here for a second. S, we've defined up here. So we can substitute this in. So this gives us our derivative with respect to our resident trait of our selection gradient, which is dw dxm, evaluated at xm is equal to xr. And this whole thing then is evaluated at xr. Our resident trait is equal to our singular strategy. This is negative. So all I've done here is I've just substituted in the definition for S. Okay, so now we just need to apply the chain rule. So if we take this partial derivative and differentiate with respect to xr, we're going to get the second order partial derivative with respect to xm and xr. The order of these things don't matter. These are then evaluated with xm and xr both equal to x star. And then we need to add to this our second order partial with respect to xm. Again, evaluated everything at this singular strategy, and then multiply that by the derivative of xm with respect to xr when xm is equal to xr. And this all has to be negative. This here is, we're evaluating this as xm is equal to xr because we're going along that main diagonal, right? Xm are going to be equal to xr. This here is just going to equal 1. So that's nice. That's just going to disappear. Does anyone recognize what this is? E, exactly. Yes. So this is just our evolutionary stability. So we see that evolutionary stability and convergent stability are not entirely independent of each other because convergent stability is affected by evolutionary stability. In a sense, you can think of that E, if we just go all the way back up here for a second, that E is telling you about the curvature of this invasion fitness, right, at our singular strategy. The steeper or the stronger the curvature is here, the more of a peak this is, if you like. The more negative this term is going to be here, and so it's going to make it more likely that it's convergent stable. However, you can choose functions, and depending on what you've got, you can choose functions and singular strategies potentially where this could be greater than the absolute value of this, in which case you could end up with something that is potentially evolutionarily stable, but convergence unstable. Likewise, you could end up with something, if this was negative and this was positive, you could have something that is convergence unstable, or sorry, convergence stable, but evolutionary unstable. Or they could both have the same. So essentially these things, while not entirely independent, you can get all possible scenarios. We'll come back to that in a moment. One thing to note here, I mentioned earlier as well, is that on our main diagonal, when xm is equal to xr, our invasion fitness is equal to 0. In fact, I'll write this as xr. Just make it clear. So our invasion fitness is equal to 0. I mentioned this earlier because if our mutant has exactly the same phenotype as our resident, then it is neither more fit nor less fit. So it has to have 0 invasion fitness. That means that all the way along that main diagonal, this invasion fitness is equal to 0. Therefore, its derivative is going to be equal to 0. Its second order derivative is going to be equal to 0 as well. Okay. So I'm probably going to run out of space here. So I'm actually going to write it up here. What we're going to do is we'll calculate our second order directional derivative along this second order directional derivative of invasion fitness along this main diagonal and set it to 0, therefore. Okay, because because there's no change in invasion fitness, the directional derivative along that line has to be equal to 0. Yeah. We're doing this ultimately because it allows you to eliminate this cross derivative, which in some circumstances can be beneficial. Okay, so that's why we're kind of going down a little bit of a rabbit hole, making it a little bit more complicated, because sometimes it can make things more simple. Okay, so how do we work out our directional derivatives? First of all, let's define a unit vector u in the direction of this just put it on the outside, 1 over root 2, 1, 1. So this is just a unit vector pointing in the direction of that main diagonal at 45 degrees. Yeah, along the line xm is equal to xr. And our gradient vector of w is just going to be equal to the vector composed of its partial derivatives, dw dxm and dw dxr. Okay, so let's work out our first order directional derivative, capital D sub u. So this is in the direction of u, of w. So just to make sure it's clear what we're doing here, if we go back to this pip, we're on this main diagonal. Our vector u is a unit vector pointing in this direction, and we're finding our directional derivative, our first order directional derivative in this direction, and then we find our second order directional derivative. Okay, that's all we're doing. And we know that these have to be equal to 0 because there's no change in invasion fitness along that line. Okay, so to find our directional derivative, can anyone remember what we need to do? I've got a unit vector and a gradient vector. Can anyone remember how we then find our directional derivative? Essentially so we've already rescaled our unit vector here, or our vector in the direction of this line so it's a unit vector. So that's the first thing that we need to do. And then everyone's racking their brains to remember what they learned in 151 or 152 or 155, right? We take the dot product of these things. Okay, so we take our gradient vector, we take the dot product with u. This is just going to give us 1 over root 2 times by the sum of the partials. Okay, that's the first order partial derivative. We actually want our second order partial derivative, which is just going to be the gradient of this dotted with u. So we have the gradient of this directional derivative dotted with u again. Okay, this will give us our second order. Second order directional derivative in the direction of u. So immediately we can see, because we're taking a dot product with u again, we're going to have another 1 over root 2 out the front. So we're going to have a half out the front, 1 over root 2 times 1 over root 2. And then we are going to have our derivative with respect to xm times by this thing in brackets here, dw dxm plus dw dxr. And this is going to be added to our partial with respect to xr of the same thing again, dw dxm plus dw dxr. This thing gives you a half of second order partial with respect to xm plus, so that's going to come from, let me highlight these to make sure it's clear. So we're going to have this term here. It's going to give us this term here. We are going to have 2 times the second order cross derivative with respect to our mutant, with respect to our resident. This comes from, this 2 here comes from this term here and this term here. And then finally, our partial, second order partial with respect to XR is just the remaining terms. This here. Okay. And I said before that this has to equal 0. Because we have this up the top here. Along this line, when xm is equal to xr, there's no change in invasion fitness. Therefore, the directional derivatives in that direction are both going to be 0. Our first order, our second order, and so on. Okay, you're probably thinking, why are we doing all of this? That's a reasonable question. I'm going to relabel, rather than writing these out continuously, I'm going to relabel these as alpha 2 times by beta and gamma being equal to 0. And note up here, this cross derivative here was our beta. And then this second one here is just the same as gamma. Note also, by the way, this is true at any point along this line. Xm is equal to xr. We're going to evaluate this at our singular strategy x star. Okay. This is assuming evaluated at our singular strategy x star. From up here, we have beta plus gamma must be less than 0 for us to be convergent stable. That means we can eliminate our cross derivative now. If we just double this first one up here, so multiply this by 2, we'll get, let's change color again. We'll get 2c is going to equal 2 beta plus 2 gamma. And that has to be negative for us to be convergent stable. We can then substitute in from this equation here, 2 beta is going to be equal to minus alpha minus gamma. So 2c is going to equal minus alpha minus gamma plus 2 gamma. That's to be less than 0. In other words, that implies that 2c has to be equal to gamma minus alpha, which has to be less than 0. In other words, back in our in the context of these second order partial derivatives, we need our second order partial with respect to our mutant trait, this was our gamma, to be less than our second order partial with respect to our resident trait, which was our alpha, for convergence stability. So depending on the scenario, you might find that it's easier to calculate this. Okay, these are, I haven't written in here, these are evaluated at our singular strategy. Okay. I'm just going to put here, so that's clear. At X star. So in some circumstances, it might be easier to work out. This is your evolutionary stability already, your E. It might be easier to work out this partial than it is to work out the cross derivative. So you could use either that condition or this condition up here, they're equivalent, to work out your convergent stability. It all really hinges on how difficult it is to work out this cross derivative or how easy it is to work out the second order partial with respect to your resident trait. There's 2 ways to do it. What this tells us, though, intuitively, though, is that the curvature of our invasion fitness, W, with respect to, because this is a 2-dimensional trait. Sorry, yes.
Like alpha and gamma accidentally been switched there because you want gamma smaller than alpha, right? It's X.
Oh, sorry, I've let's just go back to my notes to make sure it's not incorrect in here. It is beta plus gamma. Yes, I've switched them around. This is beta plus gamma here. I've probably written this in a slightly confusing way. I'm going to obviously the same thing, but yeah. I think it's because in my notes I've written it down the other way around. Okay, so you still got your gamma now as your second order partial with respect to xm. Yeah. So this gamma here, this is gamma, and this is your beta. Yeah. Thanks for pointing that out. Okay, so W, remember, is just a function in R2. Just 2 dimensions. So you can think about its curvature in sort of the direction of one of these traits xm or in the other xr. So you can think about the curvature in those different directions. And this is really just saying the curvature of your invasion fitness with respect to your resident trait, so in that particular direction, has to be greater than the curvature of your invasion fitness with respect to the mutant trait. This ensures convergent stability. This is all this is essentially saying. For me, personally, I find that kind of hard to visualize. Some people might find that easier to visualize. Any questions? No?
These can be positive, right? As long as second partial derivative is with respect to xm is less than xr.
Exactly. If they're both positive, though, this is your E, remember? So yes, this tells you then, for example, that something can be convergent stable, but not evolutionarily stable, because these could both be positive. Yeah. Okay. So I said, these ideas of convergent stability and evolutionary stability are somewhat independent of each other. They're not entirely independent of each other, but you can have all possible combinations of singular strategy being convergent stable or unstable and evolutionarily stable or unstable. Okay. So what does this mean? Well, I mentioned this idea of fitness maximum, fitness minimum being analogous to like a mountain peak or a valley. Evolutionary stability just basically means that a singular strategy is at the top of a mountain, if you like, a fitness maximum. So you can't locally, if you're stood at that mountain, you can't take a small step and increase your fitness, okay, because you're already at the top of the mountain. So nearby mutants always have lower fitness if we're evolutionarily stable. So what does that look like on a pip? Well, let me just sketch these out. Our pairwise invasion plots that we had before look like this. Our mutant, sorry, I've done that around the wrong way. Our mutant trait is on the vertical axis and our resident trait is on the horizontal axis. We always have this line here going along the main diagonal. Xm is equal to xr. I've written this on xm is equal to xr. You don't have to write that on every time. I'm just putting that there so you know. So for example, if I were to ask you to do this in like an assignment or exam or project or whatever, you don't need to write that. Let's suppose it just looks something like this, like we had before. And let's suppose we've got these positive and negative regions and a singular strategy here. And I'm going to copy this so I don't have to do it all out again. And consider 2 different versions of this. Okay. If you imagine drawing a vertical line through that singular strategy, just consider this left one for now. What does that mean? Well, I've just said about thinking about our invasion, the curvature of our invasion fitness, right? This is basically saying here, on either side of this singular strategy, our mutants, whether it's a higher trait value or a lower trait value, has lower fitness. We're always in this negative region. So that tells you it's uninvadable, right? So one way that you can just look at a pairwise invasion plot to see whether it's evolutionarily stable is to just draw a vertical line through that singular strategy. Just either side of that, are you in negative regions? If so, that means that taking a small step to increase your trait value or decrease your trait value is always going to give you lower fitness. Therefore, it has to be uninvadable locally. Okay, so in other words, if you look here, think about our W of X star plus epsilon for some small epsilon. This is going to be negative. And on this side here, W of X star minus epsilon X star is again going to be negative. This gives you evolutionary stability. E is less than 0. What happens if we flip these regions round now? And again, draw that vertical line. Well, now, if you slightly increase your trait value, so we go to W of X star plus epsilon on this side, we're in this positive region. So invasion fitness is positive. Conversely, on this side, if you slightly decrease the trait value by epsilon, again, this is going to be positive. So this is like being stood at the bottom of a valley. Yep. If you take a step one way or the other, you've increased your height. Think of the height as being your fitness. You're always in this positive region. So in this case, we don't have an evolutionarily stable singular strategy. So this one here is evolutionarily stable. This one is evolutionarily unstable. Yes.
The other line you drew is just negative X, right?
Good. I'll tell you what, so that we don't confuse this, I'm going to draw it as something squiggly. Okay. Don't want you guys to think that that is negative XR. This is something that's determined by our selection gradient. Okay. So think about, when we go all the way back up here to our PIP earlier, I talked about essentially convergent stability as intuitively being essentially this blue staircasing. Can you move in these small little steps towards this red dot in the middle? That's your convergent stability. On a pairwise invasion plot, your evolutionary stability is essentially all about this vertical line through those singular strategies. Is either side of that always in a negative region or always in a positive region? Yes.
Do we necessarily get 4 different projects, or might be more?
Things can be way more complicated than that. Yeah, you can have multiple crossing points, so you can have multiple singular strategies. Things could, in theory, just touch the line. Things, yeah, depending on the scenario, they can definitely get weird. You might also have no singular strategies. Okay. So just a reminder here, evolutionary stability on the left, because E is less than 0. In other words, the curvature here, this is ensuring we have a fitness maximum. This is a fitness minimum. So it's evolutionarily unstable. Okay. I think it's probably a good time for a break. Let's reconvene in about 10 minutes. Okay. Okay, let's start up again. Okay, so I mentioned these different types of singular strategies at the start, very briefly. But because we've got evolutionary stability and convergent stability can be somewhat independent of each other, or at least we can write down all possible combinations of these. We have 4 different types of singular strategy. Okay, so the first, a continuously stable strategy, occurs when it is both evolutionarily stable and convergent stable. Both of these are. So this up here on the left-hand side is a continuously stable strategy, or CSS. This is like a scenario where there is a mountain and there is a path that leads to the top of that mountain. Okay, so you can reach this fitness peak and you can do that through gradual steps. Okay, so that's we're able to converge towards this fitness maximum. Once you get there, you stay there because you're at the top of the mountain. You can't go any higher. Remember as well when I say that we're talking about moving locally. So there might be another fitness peak, another mountain that is even higher. but these are locally attracting. Okay, so because mutations are small, you can't suddenly jump to the other mountain. You'd have to decrease your fitness before you can go up the other side. Okay, you can essentially get stuck at a lower peak. That's a CSS. Next, we've got a repeller, which is the exact opposite. It is neither evolutionarily stable or convergent stable. And this is like the scenario on the right-hand side here. So this is a fitness minimum, and you just move away from it. Yes?
So will it be greater than or equal to 0 or just strictly greater than 0?
Strictly greater than. I mean, in all of these cases, really, we're talking, like, I would tend to avoid talking about the 0 cases just because they're just not very biologically plausible. Or any case where you essentially sit on a knife edge isn't biologically plausible, because as soon as you change one tiny thing about the system, you're going to be put either into something that's stable or unstable. So in just the same way as when we're talking about dynamical stability in an ODE system, I'm not going to focus on those knife edge cases essentially because they're not biologically plausible. Okay. But yeah, technically you could say it's convergence unstable if C is greater than or equal to 0. It's just you end up with the equals 0 kind of blurs things a little bit, and we're just going to avoid those cases. Okay. Okay, so that's a repeller. So that's like a fitness valley, and you always move away from that lowest point. There's paths that lead away from it in both directions here. This can actually, we might get to this at some point in this course. Suppose this happened to be bounded, so that suppose your X values could only say go between some positive values. So say something like body size. Okay, so you can't have a negative body size, you can't even have a 0 body size. There's going to be a lower bound on this, and maybe there's some kind of upper bound on body size as well. Or it could be any trait. It could be something that goes, it could be how strongly, let's do something like sex ratio. Okay, so sex ratio, what proportion of your gametes do you produce that are going to be male or female, essentially. That has a minimum of 0 and a maximum of 1, right? So it's bounded. In this scenario here, although these aren't, if these were our sort of boundaries of 0 and 1, here, this kind of repeller is interesting because it can produce something called bistability. Depending on which side of this singular strategy you start on, you either get driven down here or you get driven up here. We'll hopefully come back and revisit bistabilities if we have time later in the course. But repellers can be kind of interesting for that because it all comes down to your initial conditions. Where you start off can drive you into different directions. Okay, Garden of Eden is where things start getting weird. This is something that is evolutionarily unstable. Sorry, evolutionarily stable, E is less than 0, but is not convergent stable. Okay. This is a slightly weird scenario. It's evolutionarily stable, but not convergent stable. What does that mean? Well, remember, evolutionary stable is basically saying it's uninvadable. So that's like it being the peak of a mountain. Okay. If you're at that peak, you can't increase your fitness. However, it's not convergent stable. So that's like saying there's no path that leads to the top of that mountain. You can't attain it through small mutations. If you were able to have big mutations, you could potentially jump all the way to the top of that mountain. But there is no path that leads to the top of this mountain. That's why it's called Garden of Eden, because essentially if you start there, in sort of the biblical sense here, if you start in the Garden of Eden, everything is sort of fine. As soon as you move away from that, you can never go back there. This is biologically not very realistic. And it functionally essentially behaves like a repeller. Yes.
So how can you start there if you can't build up there?
Well, that's why it's sort of, in some sense, more of a mathematical oddity. That technically, if you happen to start with exactly those conditions, then it would be optimal. Okay, let me take an example of, let's think. It's kind of weird to think of an example of this, but essentially, yeah, just your starting conditions just by default happen to be the optimal. I mean, it could be something like sex ratio, maybe, just through patterns of segregation, that it happens to be that 50-50 is the optimal, right? However, if you were to perturb that population enough away from that, it wouldn't then say be able to get back to it. That would through fitness alone. It is kind of a weird one. That's why I've said this is where things start to get weird with Garden of Eden. Out of all of these, I say this is the most biologically unrealistic scenario. And in a sense, if you ever simulate this, these two things behave identically, with the exception of if you happen to start exactly at that scenario. So this is, again, a knife-edge scenario, Garden of Eden, right? If you happen to start exactly like that, think of it as well a little bit being like, if you balance a ball on top of a bowl absolutely perfectly, and technically that's an equilibrium, right? And it will stay there indefinitely. However, if you move it off, then it rolls away. That's kind of like the scenario. Okay. The last one here, an evolutionary branching point, is a point that is evolutionarily unstable. Again, this is kind of a weird one, but is convergence stable. This is where things get really weird, but biologically plausible. So it's evolutionarily unstable. So does that mean it's like a mountain or a valley? Valley, right? So everything around it has higher fitness. However, if you start near it, you converge to it. Right? That doesn't seem to make any sense, right? The reason this doesn't seem to make any sense is because you'd be like, well, surely if you're near it, you've got a higher fitness, so you'll move away from it, right? Wrong. The landscape analogy kind of breaks down because, when you walk through a landscape, usually, you're hiking in the mountains or valleys or whatever, the landscape around you is not changing. So the landscape analogy works quite nicely for these first three, not so much for this last one. What's really going on in adaptive dynamics is we go all the way back up to our invasion fitness. Just go to an earlier one. Here. The key thing is this second term here. What is the invasion? How well does this mutation fare in an environment created by the resident? So the key thing here is that every time that resident is updated, the environment is changing. So you're not really walking through a fixed landscape anymore. It's more like you're walking along like a trampoline. And as you're walking along that trampoline, this landscape is changing as you're moving, right? So as you move through it, you affect the environment. Therefore, what really goes on with an evolutionary branching point is from a distance, it looks like a mountain peak. So you're walking up towards that mountain. As you're walking up towards that mountain, it starts off looking like this, but as you get closer to it, it changes and then becomes a valley as soon as you get there. This is probably the hardest one to get your head around, but is also a really important one because it tells us that once you get to this singular strategy, you move towards it. Once you get there, you have a scenario that looks a little bit like this, where mutants on either side can invade. This then sets up the possibility that we can get diversification. So, lots of evolutionary biology is trying to understand the patterns that we see in the natural world. Why do we see, polymorphism? So different types being able to coexist. Why do we get things like speciation? All these kinds of things. Why do we get so much diversity? What processes can generate diversity? Well, in this framework, the only process that can generate diversity is an evolutionary branching point. Yes.
Does that mean that the tree will always be moving around generally?
In what way do you mean? Sorry.
Like around that evolution, like around that singular strategy, would it always be like moving a small distance, either like plus epsilon or minus epsilon?
As in for the branching point?
Yeah, because it won't kind of like go there, right? Like it
So-
won't stay there, so it'll always be moving.
Very good question. Very good question. These pairwise invasion plots are, if you note, they're two-dimensional. So we've talked up until now always about when a mutant tries to invade, either invades and replaces, or it goes extinct, right? And then you just start back with your resident. When we get this process of diversification, we'll talk about something called mutual invasibility in a future lecture. It basically ensures that actually now the mutant can coexist with our resident, say, or two mutants nearby can coexist. That means we're no longer in two-dimensional pips. We're actually going to 3 dimensions now. So it changes the setup. So very, very good question. It's a little bit more complicated. Like I said, we need to build up a little bit more until we get to this point of talking about branching in more detail. But yeah, at that point, things can diverge, and I'll show you some sort of patterns of these in future lectures. But yeah, hold that thought for the next few weeks, basically. Well, you can think of other things in the next few weeks, but we'll come back to it. Okay, so this slide here is just summarizing everything I've just said, so I'm not going to go through that again. Does anyone have any other questions about these different types of singular strategies before I move on? Yeah.
Evolutionary branching point, is that common, or is it more uncommon?
They're pretty common when we're modeling these things, and they're often something that people look for because of this idea about diversification. Okay. This is now a bit of practice for you guys. Here are some different arrangements of pips. So they haven't all got axes on them, but on the horizontal axis is your resident trait. Vertical axis is your mutant trait. And these are in these shaded regions that implies positive invasion fitness. So for example, this one up here, this would be plus, plus, minus, minus. What I want you to do is to work through these and figure out whether they are convergent stable and or evolutionarily stable. And in which case, then you can go back to this slide here and then determine which type of singular strategy it is. So maybe I'll just go through one of these to make it clear. So I'll do this one up here that I've already sketched on. So here, if I zoom in and imagine I've got here as my singular strategy. Okay. So it's where, if you're moving, say, just above the line, we cross over and change sign. So is this convergent stable? It's not convergent stable here. The reason I know is that if I say start, change color, if I start here, if I have a mutation that is slightly higher trait value, I'm in a negative region, so it can't invade. If I'm going to have a lower value, it can invade. And so I'm going to staircase away. Likewise here, I will staircase away. So I can't converge through small steps to this one here. So this tells me that C is positive. How about evolutionary stability? I draw a line through here, vertically through my singular strategy. It's always in this positive region. So C is positive. What does that mean? C is positive and E is positive. Go back here. This is a repeller. Okay, so have a go, just familiarize yourself with these different pairwise invasion plots here and classify them accordingly. Okay. And incidentally, while you're doing that, these plots here, essentially what's happening if we're varying the curvature. Sorry, this is dxm squared. So if we vary the curvature, increases this way, so here this value is positive above this line and it's negative below this line. In this direction here, we are increasing this second derivative. Okay, have a go at working through those. And if you have any questions, just raise your hand. Okay, can I have a show of hands who's finished? Okay, I'll start going through them then. Okay, so I'll go clockwise. So here, this scenario is essentially just like the one to the left. These are my positive and my negative regions. Here's my singular strategy. It's evolutionarily unstable. And just like before, it is convergence unstable. So this is, again, a repeller. In fact, I'm just going to move around just because it's easier to do. This one is also a repeller for exactly the same reason. Okay, so again, if we draw a vertical line through, get it's evolutionarily unstable, and likewise, we would always staircase away. It's convergence unstable. I'm going to shoot down and do these now. Let's start with this one. Let us see. Here, we can see, in fact, I'll do all of these together at the same time. In all three of these cases, if we draw a vertical line through our singular strategy, we're always in negative regions either side of it. So all three of these cases are evolutionarily stable. And then likewise, if we start on the main diagonal and to the left of the singular strategy, above that main diagonal is a positive region. So we will always staircase towards that singular strategy. And conversely, if we start on the right-hand side of that singular strategy and we mutate lower, we'll staircase from the other direction. So all of these three examples here are all convergence stable as well. What does that mean they are? The CSS, continuously stable strategy, in all three of these scenarios. Okay, let's do this one next. So, draw my plus and minuses on just to make sure we're all on the same page. Okay, is this one evolutionarily stable or evolutionarily unstable? Stable. E is less than 0. Is it convergent stable? No. Just like our repellers, if I start here, I will move away. If I start here again, I will move away. So this is convergence unstable. So this is what? Garden of Eden. So you can see that this Garden of Eden is essentially a knife edge scenario between, well, knife edge is not entirely accurate. This is easy to generate in many ways. It is a knife edge scenario in the sense that you only are able to obtain this fitness maximum here if you start there. As soon as you fall off that knife edge, that's the knife edge, not the actual scenario itself. As soon as you fall off that knife edge trait value, then you move away, so you behave functionally just like a repeller. Okay, think about real biological populations. They're noisy, you know, these are approximations to real populations, right? So they're noisy, they're not deterministic. All of these things could just shift the population a little bit enough so that we're no longer actually sat at that singular strategy, in which case you move away from it. So functionally, Garden of Eden essentially behaves like a repeller. And this one up here, the last one here. So my singular strategy here, is it evolutionarily stable or evolutionarily unstable? So E is positive. Is it convergence stable or convergence unstable?
Stable.
Convergence stable. So if I start here, I'll move towards it. Likewise, converge towards it here. So you can see, once you move towards it, once you get there, like although you're converging towards it, once you get there, either side, mutants are fitter. So you can imagine in this scenario that mutants either side will be able to invade. And this is what gives us our diversification. So this is what? Yeah, so evolutionary branching point. Okay, those are essentially all for these 1D traits. These are all the scenarios that we can get. Your actual pits might look a lot more complicated. You know, if you actually put together a model, these are just kind of like qualitatively what can happen. You know, you can have scenarios that maybe look like this. So plus and minus there, maybe a minus there, and maybe it looks like that. This would be a plus, minus, right? So in this kind of scenario here, you've actually got two singular strategies. But really, all you do then is just zoom in and think of, okay, what is a pit like for this region here? And likewise, what is my pip? This region here. So you can think of each of these scenarios as just zoomed in versions of what I have on the right-hand side. Yeah. Because these are just this is, locally what is going on. Oh, sorry, I've got an extra plus there. I shouldn't have a plus there. This should be a minus. That's what the confused face was about. Sorry. So yeah, this one up here on the top right would look, this would be a repeller, and the one on the bottom would be a CSS. And just like in, normal dynamical systems, in a sort of ecological sense, you can't have two things that are convergent stable next to each other. There has to be a repeller between them. So I don't know if you remember from when you're doing your sort of ODE systems, that you can't have two stable equilibria next to each other. There has to be an unstable one between them. It has to go stable, unstable, stable, unstable. Same thing in an evolutionary sense. Because these signs are flipping, you can't have two convergent stable things next to each other. Any questions about the pips? We'll move on. Yes.
More complicated. So if we have the cross section of three lines at a singular point, so we will see that from the bottom you can get there stairways, but from top will go up.
I don't think that is possible so if you go into co-evolutionary stuff, which we will hopefully get to at the end of the course, because you're no longer in this sort of one-dimensional trait space now, because you're just going along this line, you're going along this manifold basically all the time. As soon as you have two traits evolving together, say one in a host and one in a pathogen, then just like going from a single ODE into a system of two ODEs, the range of dynamics increases, so the possible outcomes increase. So in that kind of sense, there might be pathways, and we have to then talk about, do you converge in all possible pathways to a singular strategy or a co-singular strategy in that case? Or are there pathways that take you away? So kind of is a little bit tangential to what you asked, but in a sort of a broader sense, when we look beyond just one trait, yes, you can get many more complicated things. In this sort of single scenario here, because these lines are essentially the line that intersects at the main diagonal is determined by your selection gradient, they can't be multiple things intersecting at the same point. Yeah. Okay. So we've done this in a very general sense so far today. I wanted to finish by going through or returning to our intraspecific competition model that we met a few lectures ago. And we looked at conditions for evolutionary stability, and we worked out our singular strategies and all that. What I want to do now is say, okay, what can we learn about convergent stability in this model? Okay. So if you recall, this is the basic structure of our model, where Ni is the population density of phenotype Xi. We haven't specified what this Xi is. Could be anything, body type, body size, for example. It could be some sort of preference for food, whatever it happens to be. Aij is the strength of competition imposed by an individual phenotype, so imposed on an individual phenotype Xi by an individual of phenotype Xj. So how strongly does an individual with phenotype Xj compete for resources with an individual who has phenotype Xi, say? So maybe this is, individuals with a similar body size perhaps compete more strongly with each other, or just, if this is a preference for food or a preference for mates, they compete more strongly with each other if they're more similar phenotypes. And Ki, we're saying, is our carrying capacity. If the population is entirely composed of individuals with phenotype Xi, this will tend towards the population will tend towards the carrying capacity of Ki. We're going to assume, I haven't actually got R on here as well, R greater than 0 is intrinsic growth. Right. This R doesn't actually matter at all to anything in this model, essentially. I mentioned before, someone asked about non-dimensionalization. We can non-dimensionalize this by rescaling time according to this growth rate here. So it doesn't have any effect. Okay, let's define our competition function. So this is, remember, between phenotypes Xi and Xj. And I'm going to define this as e to the minus xi minus xj in brackets, that is, to the power of 4. So we had this one previously. And the carrying capacity function, ki, which is just k of xi, is some positive constant k hat times by e to the minus xi squared. So some k hat that's positive. And k hat here doesn't matter at all. You can non-dimensionalize the population sizes according to their carrying capacities and express everything in terms of proportion of a carrying capacity. Okay, so that's our basic model. I'm not going to run through all of the analysis from scratch because this is all essentially up until a point what we've done before. So this is all from lecture 11. But if you recall, we showed our invasion fitness W of xm xr is the per capita growth rate of our mutant population when rare. And I've included this evaluated at here just to clarify that we're always evaluating this at the resonance equilibrium. Typically, I don't write that down just because it's implied. You know, we should know what we're doing with our invasion fitness. Okay, we found this to be equal to r times by brackets 1 minus e to the minus brackets xm minus xr, close brackets to the power of 4, minus xr squared plus xm squared. So, okay. I'm not going to go through the derivation of all of these because we've done them all before and it's kind of lengthy. Just going to put the highlights of the results here. We also showed that the selection gradient S of xr, which is our partial derivative of our invasion fitness with respect to xm, is equal to minus 2r xr. It's a lot simpler than our invasion fitness here, just because all of these xr's and xm's eventually cancel, because we're setting xm as equal to xr. And then we found that there was a unique singular strategy when the selection gradient is equal to 0, and that occurs when x star is equal to 0. So in this case, something like body size wouldn't make sense, unless we've already kind of like offset body size. Suppose that this was like deviation from some historical mean, something like that. Okay, so these are things that we all showed before. And essentially a mistake, this should be evolutionarily stable. So for our singular strategy to be evolutionarily stable, we had to take our second order partial derivative of invasion fitness with respect to our mutant trait, evaluate this at our singular strategy, and that has to be less than 0. And through a rather messy calculation, we found this to be minus r times by 4 x star squared plus 2, which is equal to minus 2r, which is negative because we assume that r was positive at the start. So we showed that x star is evolutionarily stable. Again, from lecture 11. So the last stage that we didn't do, which we've learned from today, is now do we work out if x star is convergent stable? So we've already narrowed down, because it's evolutionarily stable, if we just go back to our diagram up here, it's evolutionarily stable, so we have to be either, in this scenario here, either has to be a CSS, or it has to be a Garden of Eden. Yep. So the sign of C will tell us what we have. So we need to work out our convergent stability. And one way that we had this written was with our cross derivative. And I'm going to stick with that one just for now. And if you recall the second part of this, here we had a second order partial with respect to xm, and that's just e. We've already worked out what e is above. Okay, so this has to be negative. Okay. I am not gonna do, nor am I gonna make you do the actual calculation here because this gets really horrible and messy. Not the absolute worst, but it's kind of a waste of time just to calculate derivatives in front of you that are very, very lengthy. In practice, I'll say that often when I'm doing sort of these kinds of analysis in my research, I don't do these things by hand. I teach you how to do these things by hand so you understand what, like, how we do them. To get things that are a bit more biologically plausible, as soon as you start increasing the complexity of these things, generally they become a nightmare to deal with. So, you know, if I get you to do these things, for example, in like a project, I haven't decided exactly what your project is going to be yet, but it's perfectly fine for you to use software because I would be hypocritical if I didn't let you guys do it as well. So you can use things like Maple or Mathematica or MATLAB or whatever to calculate these derivatives. What you should show though is that you should show like what you are doing. Like you should show, you know, this is the condition that I am now evaluating. This is the final answer. Okay. You don't have to necessarily show all your intermediate steps. Okay. And with that in mind, this eventually turns out to be equal to 0. It goes horrendously messy, and then everything basically just cancels to be 0. It always makes you a little bit worried when you plug everything in into a computer and then everything just cancels to 0. You worry you've made a mistake. So this is messy. I shan't do it here. But this is equal to 0. Or rather, sorry, that's not entirely true. This is equal to 0 plus e. This first part here is equal to 0. So if you calculate this thing here, this comes to 0. So c is equal to 0 plus e. We've already found that e is negative. So in this case, it is also convergent stable. So X star is both evolutionarily stable, or abbreviate to ES, and convergent stable, CS. Hence, X star is what? What type of singular strategy? CSS, a continuously stable strategy. This is actually analogous. The reason it's called continuously stable strategy, you might notice it's similar to evolutionarily stable strategy from evolutionary game theory. It's essentially somewhat analogous to that. But if you recall going all the way back to evolutionary game theory, that was all just about that end state, right? So again, this big distinction between adaptive dynamics and evolutionary game theory is that we talked about, okay, can we have an ESS? That's essentially just working out this first condition here. It's analogous to that. Do we have a fitness maximum or a fitness minimum? Is this the optimal strategy, right? But it doesn't tell you anything about this convergent stability. And we see here that it's possible to have something that is evolutionarily stable, but not convergent stable. And it's possible to have something that's convergent stable, but not evolutionarily stable. So that is essentially the process that we go through. The only thing that I have missed out here in terms of the whole process is this thing here. So the first stage should always be to find your ecological equilibria, because this has to be ultimately substituted in, right? It turns out with this particular model here, everything kind of cancels out anyway, so we're all good. But this is only actually valid because we are evaluating at this point. So you would have to find your ecological equilibria, check that it is locally asymptotically stable, as we did on Monday. Then you can find your invasion fitness and proceed. So the recipe, if you like, is find your ecological equilibria, check that they are stable, find your invasion fitness, selection gradient, singular strategies, and then whichever order you prefer, but typically evolutionary stability, convergent stability. Okay, so it's kind of like a 7-stage process. Once you kind of get used to solving these things, it's fairly, you kind of get a bit of a feel for, you know, what do I do? It is a bit of a recipe to you just kind of work your way through those different stages. Okay. That's easier maybe thinking about those different stages rather than kind of like, if you're like, oh, okay, here is a problem, I want to work out what happens in the long term to this thing, well, break it down into those different stages, yeah. Okay, so the actual pairwise invasion plot for that system is shown here. So we see, in this case here, our singular strategy, these are our positive and negative regions, the same kind of setup that we had before. So shaded means positive invasion fitness. We see that our singular strategy occurs at 0, as we concluded analytically. So this is something I just generated numerically in MATLAB. We can see this purple dashed line here that it is going to be evolutionarily stable. Because in this direction we have fitness maximum. So my x star is equal to 0. And then we can see that it is convergent stable, just as we did previously, regardless whether we start with a higher trait value or a lower trait value, it will converge towards it, c less than 0. You can see why, if you can generate a pairwise invasion plot, it's usually a lot simpler to work these things out rather than having to work out these horrible second order derivatives and so on. However, there will be many cases where you can't necessarily pull out a pip, or it's a little bit too tricky to do that. Or you want to show things rigorously. Okay, we've got about 10 minutes left. So I want you guys to have a quick go at solving this problem. And yeah. I'll tell you what, you guys have a go at solving this problem. And I kind of want to leave, I'm not going to go through the solution to this here. This would say, and it's type. The solutions I'll be posting online, but I want to make sure that you've got like a full thing that you can work through in your own time if you don't get to it. So start working through it now. Feel free to leave if you want to, but also I'm going to stick around for the next 10 minutes in case you have questions as you're working through it if you want to do that. Okay? Yes.
Why would a pip not be reduced?
Let me just leave that up there for now. In the sense of like, yeah, I mean, you should always be able to generate a pip. I said you can't always generate a pip. That's not entirely true. It becomes harder when you go into these like more trait dimensions, because then you're like, well, okay, how do I then draw these things? Mm-hmm. Here we're still working in one dimension. Sometimes actually looking at those second order partials can give you a little bit more information about what's actually going on. So people tend to do that a bit more than the pips. I guess it's somewhat analogous to like anything in math where you can have a geometric kind of or graphical interpretation versus there's an analytical solution or a numerical solution to that potentially, right? You know, you could, look at a quadratic and be like, well, it's clearly got a maximum or it's clearly got a minimum, right? Or you kind of want to maybe say something a bit more about it, and you can sometimes do that through like showing things analytically. So yeah, if you should be able to go back and forth between the two things, basically, is kind of the key. All right, that's what I would expect. Oh yeah, sorry, yeah. These should be xj minus xi, if I remember rightly. Yes. Thank you.
A of x star would be that you were previously.
Sorry?
So a of x and x star would be what you had written previously.
Yeah, so this would be a of x and r is equal to e to the xr minus x. This one, thankfully, is a little bit simpler because we've not got powers in there, so you should be able to work this one out.